Chromatography acts as a sorting mechanism, pulling complex mixtures apart into individual components. But on its own, it cannot identify exactly what those components are. Mass spectrometry does the opposite. It accurately identifies molecules based on their mass, but if you feed it a raw mixture, the resulting data is unreadable. Combining them presents a physical conflict. As this text on hyphenated methods details, samples in a chromatographic column are highly diluted by a gas or liquid carrying them through under pressure. Meanwhile, a mass spectrometer requires a strict high vacuum to keep ions from colliding with air molecules. Pumping a pressurized fluid directly into a vacuum will immediately crash the system. To connect these environments, chemists use hyphenated techniques. The solution involves a specialized physical connection, an interface, designed to manage the extreme difference in pressure between the two tools. The success of these combined systems relies entirely on this interface. It acts as a physical buffer, removing the high-pressure carrier fluid while allowing the isolated sample to pass safely into the vacuum chamber for analysis. Let's look at how this works for gas chromatography, or GCMS. As the excerpt explains, the gas stream exiting a capillary column can be directed directly into the inlet of the mass spectrometer's ionization source. Managing volume is the engineering challenge. The interface strips away the lightweight helium carrier gas. Heavier analyte molecules carry forward into the high vacuum chamber. Here, a 70 electron-volt beam bombards the molecules, knocking electrons loose and creating the positive ions required for analysis. Because the sample must be vaporized without breaking apart prior to ionization, GCMS is the standard choice for compounds that are highly volatile and thermally stable. Consider the physical properties we just covered. Why does a non-volatile protein require an LCMS system rather than GCMS? By managing the abrasive volume expansion and ionization out in the open atmosphere, the LCMS interface completely bypasses the risk of flooding the internal vacuum. This chart displays mass spectra for tetrahydrofuran using different ionization modes. During a chromatographic run, the spectrometer scans constantly, assessing masses multiple times per second. As a mixture exits the column, the instrument records thousands of individual mass spectra like these. To make that massive amount of data readable, the software generates a total ion chromatogram. It takes every ion detected in a fraction of a second across all mass-to-charge ratios and adds their intensities together. That sum becomes a single data point on a new timeline. This process flattens a complex three-dimensional set of data into a straightforward two-dimensional map, showing exactly when distinct compounds exit the column. In practice, the analyst uses this simplified chromatogram to count the individual components in the mixture. Clicking on any one peak reveals the raw data hiding underneath it. This figure shows the mass spectra for ethanol and 1-octanol. Selecting a retention time reveals the exact fragmentation pattern of the isolated compound. The system cross-references this pattern, like ethanol's base peak at mass 31, against digital libraries to provide a definitive identification. The choice of instrument dictates the workflow. You use GCMS for volatile samples, employing vacuum interfaces and electron ionization. You use LCMS for fragile liquids, relying on atmospheric pressure ionization to protect the internal systems. By carefully engineering the space between high pressure and hard vacuum, hyphenated systems turn a separation column into a precise tool for identifying components of chemical mixtures.